Hello and welcome to another Java tutorial. We are going to continue our discussion on returning values from a method. And we saw that, for example, if you look at this method getArea, which is a non-static method, it has access modifier, and then it has a return type, and then the compiler enforces that you have to return some expression, right? That evaluates to a value to a type that is compatible with this int type. And obviously it can be a byte, short. It cannot be long because long doesn't implicitly convert to int, for example. And we saw a very interesting case when polymorphism is in action, which means the return value is not a primitive type, it's a class type or an object, or basically a non-primitive type, right? A class type, it could be an interface type, etc. And we said because classes can extend other classes or implement other interfaces, so a particular class can have super types, which means a super class or super interface. And we saw that polymorphism allows you to return a subtype even if the method declaration declares a super type. This method returns the integer that expression evaluates to. So again, in our discussion of the fundamentals of Java language about the return statement itself, we said that we can put any statement here. And the compiler or the JVM first evaluates the expression, and each expression has a return value that the type is also clear to the compiler and JVM, and then it has to be compatible with that, right? The getArea method returns a primitive type. A method can also return a reference type. For example, in a program to manipulate bicycle objects, we might have a method like this. So we have a method that has see who's fastest. It takes like a couple of two bicycle types and then an environment, and then returns a bicycle type, and it declares a local variable bicycle fastest, and then some code to calculate which bike is faster given each bike's gear and cadence. So we have access to the state of the bicycles, and we can see the information, and then eventually we have a fastest, right? Now this is, again, when you type something like bicycle fastest semicolon. Unlike C++, in Java, this doesn't create an object. It doesn't call the, for example, the default constructor of the object bicycle. It doesn't do that. This is just declaring a variable, and the default value is null. And we said that in local variables, Java compiler doesn't initialize them. So at the moment, this code won't compile, because if you just write it like this code won't compile, because you're just declaring a local variable that hasn't been initialized, and you cannot return an uninitialized variable, a local variable from a method. Basically, after this line of code, if you don't do anything with this variable, then the compiler, if you don't initialize it, the compiler won't allow you to do anything with this variable, right? You have to initialize it, and even null initialization has to be explicit for local variables. You have to say equals null. That's the explicit initialization of local variables. And again, for the fields of a class, we saw that this is not the case. JVM will guarantee that it's going to initialize all the fields to the default values. So you don't need to write bicycle fastest equals null if this fastest, for example, is the field of a class. But local variables, there is no guarantee of default initialization. They will not be initialized. You are responsible for initializing. So returning a class or interface. If this section confuses you, skip it and return it after you have finished the section on interfaces and inheritance. We already have looked at interfaces, and we have also looked at the inheritance to some extent. So we're going to continue with the discussion here. When a method uses a class name as its return type, I mean class name, we're saying class name, but it's actually a type. A type can be a class, interface, enum, etc., right? So every method has to declare a return type, such as see who's fastest does. The class of the type of the return object must be either a subclass or the exact class of the return type, right? And again, this goes into the topic that we discussed in the previous lecture, which was the concept of polymorphism for the return type of the methods. We saw that the variable, what you're returning from a method, doesn't have to exactly match the type that you declare. When you declare the method, it has to be compatible. And we saw that, for example, for primitives, a float is compatible with double, right? Because a float can be implicitly converted to double without the loss of data, right? without the actual truncation of the bits in the memory, because double is 64-bit, float is 32-bit, so you can comfortably put 32-bit or fit 32 bits into 64-bit. Same with reference type or pointer types, and this went into the concept of object slicing, which meant that every subclass has a slice, which is its superclass, or basically the state of the every subclass. Part of its state is actually the state of its supertypes. And we said that interfaces don't really hold a state. They don't have a state. Basically, interfaces are abstract constructs, right? So the state of a subclass basically comes from the state of its superclass. So, and then this line of code compiles. We can create an object of a new mountain bike, for example, and we know that this new operator returns a pointer that is pointing to this mountain bike, to a state of this mountain bike in the Java heap, right? Because we are initializing some data, some fields, and then those are held somewhere in the Java heap, right? But then we said that instead of assigning this returns a pointer or reference to that type, instead of assigning it to the reference of type mountain bike, we can assign it to a reference of type bicycle, which is a super type of mountain bike. And this works fine. And B1, you can think of it, we are slicing the state of this mountain bike with this superclass. So basically, this is like B1 is pointing to the state, that part of the state of the mountain bike that is related to its super type bicycle. And the reason this works is that there is a guarantee that the Java compiler enforces, and that's this line of code. So this is a guarantee that Java compiler enforces, which is that the job of the constructor, we've seen that the job of the constructor is to initialize the state of your class, your object, right? So the job of constructor is to initialize the state of the class or object that we're creating of this type. And we said that in order to be successful, because part of the state of the subtype is the state of the supertype. So when we are initializing the state of the subtype, we have to guarantee that the state of the supertype or superclass is initialized first, because these are related. That's why Java compiler enforces that the first line of code in the constructor has to be a call to one of the superclass constructor. Then, because we are calling a constructor of the superclass, which it means we are actually initializing the state of the superclass via one of its constructor. And if I hit command and then click on this, it tells me which constructor of the superclass is invoked. All right. So I want to be very clear about it. This is enforced. If your superclass has a default no argument constructor, then the call to super round brackets and semicolon is explicit. So the compiler will automatically add this if superclass has a constructor like this that doesn't take any arguments. So if the superclass has a no-arg constructor, the compiler will insert that code as the first line of code implicitly. You don't have to add it. But if the superclass doesn't have a no-arg constructor, you are explicitly have to explicitly add a call to the superclass constructor and pass it the variables that the constructor of your subtype takes, or maybe some other values. So you have to pass some values here to initialize the superclass constructor. All right, that's why polymorphism works. And then if you create an object of this type, mountain bike, and assign it to the pointer or a reference type of the super type, this pointer is pointing to the state of the superclass, which has already been initialized, right? And it has access to all the methods of the superclass. So we are slicing the state of the subclass and the methods. And again, subclass gets all the public or protected methods of the superclass. It might also add its own extra methods here, for example. But then when we slice it through this polymorphism thing, then B1 can't have access to the methods that the subclass provides, because it's really pointing to a bicycle object, right? When we said that there is a concept called casting, and in this case we are actually downcasting, which means we cast a superclass pointer to a subclass pointer, and then we say that hey, this B1 was actually pointing to a mountain bike object in a Java heap, but then we slice it, but it's possible to slice it back. And this is kind of like a safe cast. There are also some unsafe casts that we will talk about later when we discuss the concept of casting. But I just want you to quickly show you the bytecode for this kind of casting behavior. So if we go here, we go to the classes. Let's look at the bytecode for return polymorphism. Open with class file viewer. And let's see. So we have a test1 method here. Let's zoom in. And so we're calling the new operator, and we duplicate the reference and then iconst1. Remember, these are constants, and we saw that -1, 0, 1, 2, 3, 4, 5. These literal integer literals have hard-coded bytecodes. Iconst1, iconst0 for the second one, iconst1 again, and iconst2. These are the actual literals, right? That they have dedicated bytecodes, hard-coded bytecode. And then invoke a special. We are invoking a special method, which is a constructor that takes int, a store 0, which is the reference 1. We're storing at the first location of the stack. That's because this is a static method. And then we are going to access the B1 again. So we have to load it again from location 0. And then check cast. So JVM actually at runtime does the casting, right? So there is a check cast bytecode to make sure that this casting works, because let's say you can always cast to some other type. For example, let's say you want to cast to car, for example. I guess we want to import it, so I'm going to use a fully qualified name. All right. And let's use it also here. I don't want to add the import statement at the moment. I just want to show you that we can actually do casting, cannot cast from bicycle to car. So the compiler warns you that this casting won't work. Let's see, test1 8th row. So as you can see in the bytecode, the compiler is throwing an exception saying that something is wrong with this code, right? So we cannot cast from a bicycle to car, for example. That doesn't work because these types are not related. But sometimes you can cast, the cast is allowed, but it's not a safe cast. And so the casting might still not work. And that's when you try to cast from so unsafe cast is when, for example, you try to convert super type to subtype. This won't work, even though the compiler probably doesn't. We can try it. So let's say we create a bicycle, B3, and we know that the bicycle has its own constructor, right? A start cadence, etc. Let's say 10. So let's say 101, 101, something like this. So we can actually create a bicycle object by itself, but then we can say mountain bike B4 is B3. This is not going to work. The compiler doesn't allow you to assign a pointer to a super type directly to a subtype because implicit conversion is not allowed. But what if we try to force it? We force a cast, right? This is a forced cast. So this is an unsafe cast. That's because the compiler warned us that, hey, the compiler refused to do the implicit conversion of the B3 variable of type bicycle to a subtype. But then we forced it. So we're saying that, hey, we're telling the compiler we know what we're doing. So don't worry about it. Go ahead and do the cast. And then there is a check cast here. So, and then let's see if this code runs. So if I run test1, let's see what we get. We get an exception, class cast exception. Bicycle cannot cast to class mountain bike, right? Basically, we get a class cast exception. This unsafe cast won't work. So we didn't get a compilation error because we forced the compiler to do the cast for us, right? And the compiler said, okay, I just tell the JVM, the compiler said, okay, I go ahead and compile this code, but I put a check cast for the JVM at runtime. When you run the code, I ask the JVM to check that to make sure that this casting works. Because this was unsafe cast, I refused to do the casting, I refused to compile, but you forced me to compile it. So I'm going to compile it, even though I didn't want, but you forced me to compile it, no problem. But I just put a check cast for the JVM so that the JVM doesn't double check. And at runtime, you have no power over JVM. So if JVM sees that this cast doesn't work, your application is going to crash. And the Java compiler says that I'm not responsible, you forced me, so you have to deal with the consequences. If you force the Java compiler to do something that the Java compiler doesn't want to do, you have to live with the consequences. You are responsible with the consequences at runtime, right? The Java compiler is smart enough to ask JVM to double check it, and then there is no way for you to escape this check cast, right? Whenever you're doing casting, JVM has to be sure that casting works at runtime, otherwise your application crashes. I mean, if you think that the casting is not going to work, maybe this is a type that is provided at runtime, and that happens. Sometimes the type is provided dynamically at runtime, and when we discuss a very advanced topic of Java, which is lazy loading of class files, which is what JVM typically does, you can actually have types that are not available to the compiler at compile time, but they will be available at runtime on the class path, and you can load them. Because whenever you want to create an object of some type, you have to first load the class file that is associated with that type, and then you can go ahead and invoke the constructors. We will see example of this advanced topic when we talk about Java reflection, for example, and how you can do it. But for now, remember, forcing the compiler to do something that it doesn't want to do has consequences at runtime. And there might be a case when JVM decides that whatever you decided to do and force the compiler is not going to work. For example, in this case, an unsafe cast, and then your application crashes. So there is a check cast bytecode instruction to make sure that things would work, casting would work. I'm going to comment this out for now. And then let's go back and continue our discussion here. Okay, suppose that you have a class hierarchy in which imagine number is a subclass of Java lang number, which is in turn a subclass of object as illustrated in this figure. So we have object at the top of our inheritance hierarchy, number, and then imaginary number, the class hierarchy. Now suppose that you have a method declared to return a number, and we know that if this method can declare a class of type or a type number or any subclass, imaginary number, because subclasses are compatible with superclass, you can slice them. The return number method can return an imaginary number but not an object, right? Because number, if you return an object, you can't slice object into a number, because basically they're not compatible. You cannot convert a super type into a subtype, because essentially what happens is exactly what we saw. There is a casting happens, right? So it becomes basically in the bytecode. Let's see. So what I'm going to do here, let's see what happens in the bytecode. If I change this B1 to mountain bike, all right, or maybe let's comment it out, let's copy it and do it again. So I'm going to comment this out. I'm going to comment B2, and I'm going to set B1 to mountain bike, right? But then the method returns a bicycle. Now what's going to happen in the bytecode? You can probably guess what's going to happen. The bytecode is going to be exactly like casting. So basically the bytecode is going to be this return B1 is going to be equivalent to first do the cast, something like this, and then basically return B2, and we can examine it, right? So the compiler is going to add some extra code that does the casting first, and then so let's try to look at this. All right, so test one. So let's see what happens here. In the test one, we are creating new the constructor a load. We load b1 and then we return it. So you kind of don't see the code that happens in terms of casting, because that is implicit in this case. So this is equivalent, but it's implicit. So when JVM sees that, hey, your B1 was mountain bike and you're returning a bicycle, JVM makes sure that this is correct. And it is correct, because otherwise your code most likely wouldn't have compiled, right? But the JVM is aware of the fact that there is a casting has to happen, and B1 will be sliced when you return it from a method. If you look at the, for example, in the basically when you return it when you return from the method call. All right, back to continuing this one. All right, so you can override a method and define it to return a subclass of the original method. And again, this is something we will look at later when we talk about overriding methods. But in general, if you have a method that is declared in a super type, you can override it. And overriding in the subtype means you declare a method that has exactly the same signature, the same name, the same parameter types, but it's in the subtype instead of super type. And we have already seen the override concept when you implement an interface, because interfaces only have abstract methods and you are forced to override them in your class and provide implementation. But then the other things that when you override, you don't need to keep the return type. The return type can be any subtype as well, because object slicing works. Any subtype is a type, is a compatible type with the super type. This technique called the covariant return type. So we're going to put it, I called it polymorphism, right, for return type. It's also called covariant. Covariant means they can co-vary with each other. So you can replace a subtype for a super type. Still works fine. Later you see that even a super type such as interface is valid, and you can create a class which has a super type of interface, and the return type of the method is interface. And one of the best practices is always program to interfaces, because they abstract constructs, and it's best to so that the return type of your methods are kind of abstract constructs like interfaces. So that's one of the best practices of Java, is always try to program to interfaces. Covariant return type means that the return type is allowed to vary in the same direction as the subclass. This just means polymorphism is allowed. It works. Object slicing works. The state of a subclass, part of it is the state of the superclass, and you are always allowed to slice it. You are always allowed to slice the state of a subclass into the state of its superclass part, and that's called the covariant return type. Note, you can also use interface names as return types, because interfaces are also supertypes of a class. In this case, the object returned must implement a specific interface, which means the object that you return must be a subtype of your interface, right? That interface has to be a supertype. All right, I hope you enjoyed this lecture and now have a very good understanding of the polymorphism or covariant return types, what kind of types you can return from a method, and then what happens inside the body, and what kind of variables you're allowed to return. Every variable has to have a type, and that type should be covariant or with the return type that the method declares. So please stay tuned, and I'll see you in the next one.